Hello everyone, thanks for coming. So now we are going to do a review of our lectures in week 3. So in this week we talk about the surfaces and the space curves. So first, in order to visualize a surface, we need the traces of a surface, which are the curves of intersection of the surface with planes parallel to the coordinate planes. Then we define cylinders. Cylinder is a surface that consists of all lines, which are called rulings, that are parallel to a given line and pass through a given plane curve. So think about the cylinder, common cylinder, which can be written as x squared plus y squared equals to 1. So this will be a cylinder in the 3D space. We have many types of quadratic surfaces, but they can all be written in two standard forms: ax squared plus by squared plus cz squared plus j equals to 0, where a, b, c are non-zero, or ax squared plus by squared plus iz equals to 0. So we talk about 5 different types of quadratic surfaces in our class: the ellipsoid, x squared plus y squared plus 2 squared equals to 1, which is similar to a ball in the space; elliptic paraboloid. So in the xy plane, it looks like a paraboloid, but in the xz or yz plane, it looks like the parabola. And then the hyperbolic paraboloid, the hyperboloid of one sheet, the hyperboloid of two sheets, which is a disconnected version of the hyperboloid of one sheet. So basically, different coefficients will determine the property of the quadratic surfaces. Then we discussed space curves. Space curves can be characterized by vector functions, which are functions with a vector output, vt equals to ft, gt, ht. We can take the limit. The limit exists only when the limits for the 3 components exist. Similarly, we can define derivative. The derivative is just to take the derivative for the 3 components. Finally, the integration. The integration is also to take the integration for all 3 components. We have some differentiation rules, and the differentiation rules are just generalizations of the differentiation rules for the scalar valued function, like the additivity, homogeneity, and the chain rule, and the dot product. The differentiation rule for the multiplication of two functions, the dot product and the cross product, and finally the chain rule. Finally, we talk about some geometric quantities for space curves. For a space curve characterized by RT, we can define the arc length to be the integration of the norm of r prime t. This is also a natural generalization of the arc length for plane curves. The unit tangent, capital T of t, which is r prime divided by the norm of r prime. The unit normal, sorry, here there is a typo. N of t should be t prime of t divided by the norm of t prime of t. This should be t prime, not n. And then binomial is the cross product of t, the unit tangent, and the unit normal. Finally, we define the curvature of a curve. The curvature is actually the norm of the changing rate in the unit tangent divided by the norm of r prime. Also, sometimes we define it as the norm of r prime cross r double prime divided by the norm of r prime cubic. Thanks for listening.